The moon lacks an atmosphere to retain heat, resulting in sudden temperature changes. Daytime, up to 127 degrees, hot enough to melt certain metals. Nighttime, down to 173 degrees, cold enough to freeze any uninsulated equipment. Equipment is prone to damage due to uneven expansion and contraction of materials. Thermal regulation systems consume significant energy to maintain balance. Without an atmosphere or magnetic field, the moon's surface is directly exposed to high-energy cosmic rays from space, ultraviolet rays from the sun, which are harmful to both humans and equipment. Without an atmosphere to burn up meteoroids, even tiny particles can cause severe damage. Spacecraft and bases require high-impact resistant materials for protection. Low average temperatures. The average temperature is 63 degrees, with polar regions dropping to 125 degrees during winter. Temperature differences between day and night put stress on construction, materials and electronics. Dust storms. Mars frequently experiences massive dust storms, sometimes covering the entire planet for weeks. Fine dust particles not only block sunlight, but also erode mechanical components. Low atmospheric pressure. Mars's atmospheric pressure is only 0.6% of Earth's, making liquid water impossible on the surface. All structures and equipment must withstand the significant pressure differences between the interior and exterior to protect humans. Extreme temperatures. Common materials like steel, plastic, and glass expand and contract unevenly under sudden temperature changes, causing cracks and fractures. Large structures risk losing stability under thermal stress. Dust and micrometeoroids. Fine dust on Mars and the Moon can infiltrate small openings in equipment, causing abrasion and mechanical failure. Even small micrometeoroids can puncture solar panels or damage base surfaces. Radiation. Cosmic rays not only harm human health but also reduce the lifespan of electronic devices and construction materials. Electronic systems require special shielding to prevent malfunction or damage from radiation. Radiation exposure increases the risk of cancer, neurological damage, and long-term health issues. Astronauts must wear specialized protective suits at all times outside the base. Thin atmosphere. Humans cannot breathe without oxygen supply systems. Low atmospheric pressure can cause the body to implode without proper protection. Challenges in local production. Liquid water cannot exist on the surface, making resource extraction and utilization challenging. Raw materials like regolith require complex processing to become usable construction materials. Graphene. A lightweight, durable supermaterial that can withstand extreme temperatures and radiation. Regolith bricks. Lunar and Martian regolith can be compressed into bricks for building bases. Benefits readily available on-site, reducing transportation costs from Earth. 3D printing technology. Using local materials. 3D printers can use regolith to construct structures layer by layer, from small bricks to large walls. Automation. Reduces human involvement during the initial stages, ensuring astronaut safety. Robotics and AI systems. Robots can handle dangerous tasks like material collection, base construction, and equipment maintenance. AI optimizes operations, including temperature control, energy management, and fault detection. Smart base designs. Underground bases, utilizing natural soil as a shield against radiation and temperature extremes. Dome-shaped structures. Dome designs evenly distribute pressure, increasing structural strength and resistance to dust storms. Renewable energy utilization. Self-adjusting solar panels optimize sunlight absorption. Advanced energy storage systems ensure continuous power supply, even during dust storms or nighttime. The harsh conditions on the Moon and Mars present significant challenges but also provide opportunities for technological advancements. With solutions like advanced materials, 3D printing technology, and support from robotics and AI, humanity is steadily moving toward building sustainable bases in outer space. This journey is not only a step toward survival on other planets, but also a new chapter in human. What is regolith? Regolith is the fine layer of soil and rock covering the Moon's surface, formed over billions of years by meteorite impacts. Characteristics: gray in color, with a texture similar to sand but much sharper. rich in metal oxides such as iron, aluminum, and silicon, key components for construction. Features of regolith. Application potential. Regolith can be processed into bricks or used as a raw material for 3D printing. When mixed with a binder, it can produce sturdy and durable materials. On-site availability. Readily available on the surface, eliminating the need for transportation from Earth. Reduces the cost of delivering materials during space missions. Challenges in using regolith. Regolith particles are extremely fine and sharp, which can damage equipment if not handled carefully. Complex processing is required to transform regolith into construction-grade materials. Autonomous robots. Robots are deployed to collect regolith from the lunar surface. Equipped with sensors, they identify areas with the highest quality regolith deposits. Initial processing. Regolith is cleaned of dust and large rocks, then mixed with a special binder to enhance adhesion. 3D printing structures. How it works. The 3D printer layers the prepared regolith mixture to build strong structures like bricks, walls, or framework. High precision. 3D printing technology allows for millimeter-level accuracy, enabling designs tailored to space conditions. Fully automated. The printer operates continuously without human intervention, reducing risks during the initial construction phase. Visual demonstration. Simulated video of robots collecting regolith in 3D. Printers building structures layer by layer. Transportation costs. Transporting materials from Earth to the Moon is extremely expensive, averaging over $50,000 per kilogram. Using local regolith eliminates the need to transport large quantities of construction materials. Energy savings. Reduces the need for fuel to deliver materials into orbit. Full automation. Safety. Robots and 3D printers replace humans in dangerous tasks. Efficiency. 3D printers can operate continuously for hours, speeding up the construction process. Faster construction. Compared to traditional methods, 3D printing dramatically shortens construction time. This technology is ideal for quick builds in harsh space environments. Environmentally friendly for space use. No waste generated. The entire regolith deposit is utilized without any discarded material. Flexible adaptation. 3D printing designs can be adjusted to meet the specific needs of lunar conditions. NASA and ongoing experiments. NASA has tested 3D printing technology using simulated regolith on Earth. Lunar Base Project plans to use regolith to build lunar bases for long-term missions. These bases will include living quarters, laboratories, and storage facilities. Potential for space construction. On the Moon, regolith will be the primary material for construction, combined with solar power for self-sustaining operations. On Mars, the same technology can be adapted to Martian regolith, which is also abundant. Long-term vision. 3D printing with regolith is expected to become the standard method for space construction. This technology is a critical stepping stone for deeper space exploration. From the Moon to other planets, printing technology using regolith is not only cost-effective and efficient, but also a key enabler for sustainable space construction. With its potential applications on the Moon and Mars, it represents a significant milestone in humanity's journey to explore the cosmic radiation. Refers to high-energy particles originating from two main sources: solar radiation, energetic particles emitted by the sun, including protons and electrons, especially during solar storms. Galactic cosmic rays, high-energy particles from outside our solar system, generated by supernovae and other cosmic events. To the impact of cosmic radiation on materials. Constant exposure to radiation can weaken materials over time, making them brittle and prone to damage. Radiation can cause electronic devices to malfunction, interfering with critical systems like navigation and communication. On humans, direct exposure increases the risk of cancer, damages DNA, and affects the nervous system. Without protection, astronauts are vulnerable to long-term health issues. Introduction to space challenges. Building materials for space missions must endure extreme conditions like temperature swings, radiation, and abrasive dust. Traditional materials often fail under these stresses, making rigorous testing essential before deployment in space. Purpose of testing. Simulate space conditions. Testing materials in controlled environments replicates the challenges faced on the Moon or Mars. Ensure long-term durability. Only materials capable of withstanding harsh conditions for years are chosen for space projects. Minimize risks. Proper testing reduces the chances of failure during missions, ensuring the safety of astronauts and equipment. Overview. Space environments experience extreme temperature variations, from searing heat during sunlight exposure to freezing cold in the shadows. Testing process. Materials are placed in a temperature simulation chamber that cycles between 150 degrees and 150 degrees. The process evaluates thermal expansion and contraction, detects material deformation under temperature swings, structural integrity, measures resistance to cracking or breaking. Significance. Materials that withstand these extremes without degrading are critical for structures on the Moon and Mars. Example: regolith bricks and graphene-based composites have shown promise in maintaining integrity. Overview. Cosmic and solar radiation are constant threats to materials in space, leading to degradation and structural weaknesses. Testing process. Materials are exposed to gamma rays in controlled doses to simulate the effects of space radiation. Key aspects tested. Radiation resistance determines the material's ability to maintain strength and functionality over time. Impact on electronics evaluates whether radiation causes malfunctions in embedded systems or sensors. Significance. Ensures that materials, like regolith bricks and metal coatings, can provide adequate protection for habitats and sensitive equipment. Overview. Lunar and Martian dust is extremely fine, sharp, and abrasive, causing wear and tear on materials and equipment. Testing process. Materials are subjected to simulated Martian or lunar dust environments in a specialized chamber. Evaluates abrasion resistance measures the material's ability to resist wear and tear over prolonged exposure. Dust infiltration determines if the material can prevent dust from penetrating surfaces, and dust-resistant materials ensure long-term functionality of critical systems like solar panels, airlocks, and habitat exteriors. Test outcomes. Materials that pass these rigorous tests are approved for space construction projects. Examples of successful materials: regolith bricks, proven durable in temperature, radiation, and dust tests. Graphene composites show excellent thermal stability and radiation resistance. Metal coatings, titanium, aluminum, protect surfaces from radiation and dust abrasion. Benefits of rigorous testing. Enhanced safety. Ensures the safety of astronauts and the reliability of space missions. Reduced maintenance costs. Durable materials reduce the need for frequent repairs, crucial in remote environments like the Moon or Mars. Extended lifespan. Tested materials can endure years of exposure to harsh conditions, making them ideal for long-term bases. Technological advancements. The knowledge gained from these tests helps improve material science for both space and Earth. Applications. Rigorous material testing in simulated space environments is vital for the success of future lunar and Martian bases. By ensuring that materials can withstand extreme conditions, humanity takes another step toward sustainable space exploration. As testing technology evolves, the dream of living and working in space becomes increasingly achievable. Overview of the base design. The base serves as the foundation for sustainable human presence on extraterrestrial surfaces. Essential areas include living quarters safe, temperature-controlled habitats for astronauts to rest, eat, and sleep, laboratories, advanced research facilities for conducting experiments on regolith, soil composition, and potential resources, greenhouses, enclosed environments for growing plants, essential for producing food and oxygen, solar energy systems, fields of solar panels optimized to generate and store renewable energy, structure and layout, modular design. The base is divided into interconnected modules that can be expanded over time. Protective shielding. Walls constructed with regolith-based materials to block cosmic radiation and extreme temperatures. Underground sections to provide natural insulation and enhanced safety. Visualization. Use animations or graphics to depict the base layout. including dome-like structures connected by tunnels, solar panel arrays, and domed greenhouses for deep printing and advanced materials. 3D printing with Regolith. On-site Regolith is processed and used to print structural components such as walls and shelters. Reduces transportation costs and time by utilizing local resources. Graphene and metal reinforcements. Lightweight. Durable materials are incorporated to enhance structural integrity. Ensure resistance to extreme environmental conditions, like dust storms and radiation. Automation with robots and AI. Robotic construction. Robots handle material collection, processing, and 3D printing with precision. Automated systems can operate 24/7, ensuring rapid base construction. AI integration. AI monitors structural integrity, manages energy consumption, and performs predictive maintenance. Smart systems adapt to environmental changes, optimizing resources like water, oxygen, and power. Efficiency and sustainability. Cost reduction. By automating the process and using locally available materials, the overall cost of building a base is significantly reduced. Time saving. 3D printers and robots operate continuously, cutting construction time from years to months. Controlled environment. The interior of the base is designed to provide Earth-like conditions, ensuring the health and well-being of astronauts. Temperature control. Advanced insulation and temperature. Regulation systems keep habitats comfortable. Oxygen supply. Air is recycled through advanced life support systems and oxygen generated by greenhouses. Research and experiments. Astronauts work in laboratories, analyzing samples and testing technologies for future missions. Key areas of study include regolith usage, water extraction, and long-term food production, maintenance and upgrades. Robots assist astronauts in repairing and upgrading systems to ensure optimal performance. Leisure and exercise. Facilities include exercise rooms to combat muscle loss and areas for relaxation. To support mental health, greenhouses for sustainability. Food production. Crops such as potatoes, lettuce, and wheat are cultivated in controlled environments. Oxygen generation. Plants recycle carbon dioxide into oxygen, supporting the breathable atmosphere inside the base. Water recycling. Advanced systems capture and purify water from greenhouse condensation and waste for reuse. Visualization. Showcase scenes of astronauts working in laboratories, harvesting plants in greenhouses, and maintaining systems alongside robots. The base as a stepping stone. Testing ground for exploration. The base serves as a prototype for living and working in space, helping to refine technologies for future missions. Experiments conducted here will guide the development of more advanced habitats on Mars and beyond. Launching point for deep space missions. Bases on the Moon and Mars can act as fuel depots or assembly sites for missions to the asteroid belt and outer planets, creating an interplanetary civilization, self-sustaining communities. With advancements in renewable energy, water recycling, and food production, these bases can evolve into fully autonomous settlements. Economic opportunities. Mining rare resources like helium-3 on the Moon and metals on Mars could fuel economic growth on Earth and beyond. Global collaboration. International partnerships. Building extraterrestrial bases requires cooperation between nations and private companies, fostering unity in space exploration. Public involvement. Space agencies can engage the public through education and outreach, inspiring a new generation of scientists and explorers. Visualization. Depict a futuristic vision of bustling lunar and Martian bases, complete with domed cities, solar farms, and vibrant greenery. Show rockets launching from these bases to explore deeper into space, symbolizing humanity's limitless potential. Lunar and Martian bases represent humanity's bold step toward becoming a multi-planetary species. By leveraging advanced technologies like 3D printing, robotics, and sustainable systems, these bases will not only support survival, but also serve as platforms for innovation and discovery. The journey to establish these bases paves the way for a future where Earth is just the beginning of human civilization. Challenges on the Moon and Mars. Extreme temperatures. The Moon experiences swings from -43 to 127 while Mars averages 63 degrees. These conditions demand materials that can withstand thermal expansion and contraction. Radiation exposure. Both the Moon and Mars lack an atmosphere or magnetic field to shield against cosmic rays, posing risks to humans and infrastructure. Dust and micrometeoroids. Fine, abrasive lunar and Martian dust, along with meteoroids, can damage equipment and habitats over time, turning challenges into opportunities. These harsh conditions push humanity to innovate, developing advanced materials, energy systems, and construction techniques. The quest to overcome these obstacles is driving technological progress not just for space, but for applications on Earth as well. Regolith bricks. Local lunar and Martian soil is compressed into strong, radiation-resistant bricks, reducing reliance on Earth-based resources. Graphene composites. Lightweight, durable materials provide superior protection against radiation and extreme temperatures. Metal coatings. Aluminum and titanium layers shield habitats and equipment from environmental hazards. 2. 3D printing technology. Resource efficiency. By using local regolith, 3D printers reduce transportation costs and enable on-site manufacturing of habitats. Precision and speed. 3D printing allows for rapid construction of modular designs, minimizing human exposure to danger during the process. 3. Automation with robots and AI. Robotic construction. Autonomous robots collect, process, and assemble materials, operating continuously in harsh conditions. AI support. AI systems monitor environmental conditions, optimize resource use, and predict maintenance needs for long-term sustainability. Stepping stone for life beyond Earth. Testing ground. Lunar and Martian bases serve as prototypes for sustainable living in space. Refining technologies for future interplanetary missions. Resource hubs. These bases could support deep space exploration by providing resources like fuel, water, and construction materials. Building a multiplanetary civilization. Economic potential. Mining rare resources such as helium-3 on the Moon or valuable metals on Mars could drive economic growth. Global collaboration. Space exploration fosters unity among nations and private enterprises, creating shared goals and partnerships. Inspiration for the future. This journey is not only about survival, but also about redefining humanity's place in the universe. By stepping beyond Earth, humanity opens a new chapter in its story, one of limitless exploration and potential. The Moon and Mars present unique challenges, but they also represent unparalleled opportunities for innovation and discovery. With advanced materials, 3D printing, and robotic technologies, humanity is closer than ever to building sustainable bases beyond Earth. This bold journey is more than a scientific endeavor. It's a leap toward creating a multi-planetary civilization, marking the start of a